Hey everyone, in this activity we're going to be learning about simulations and Monte Carlo methods with R. Specifically, we're going to explore how we can conduct basic simulations using R, emulating real-life scenarios, how we can generate values from various statistical distributions useful in a lot of different settings, and how we can calculate what are called Monte Carlo estimates of parameters that we're interested in for particular statistical distributions, when conventional theoretical methods or formulas are difficult to use or don't exist. So to start, like usual, we're going to use RStudio and a Quarto document, beginning by loading some necessary R packages here. All right. So to talk about Monte Carlo methods generally, Monte Carlo is somewhat synonymous with the word random. Its namesake is a famous casino in Europe. Uh, Hence, casinos involving gambling and games of chance is associated with probability and randomness, right? So Monte Carlo methods are computational methods based on computing this wide area of statistics that can be used to estimate different values of interest, to come up with predictions, right? All based on just computer simulations, right? Based on random sampling to solve relatively difficult probabilistic problems or just uncertain questions that we would like to answer. Okay. So we can simulate or emulate all kinds of real life scenarios, ranging from very simple to quite complex, using Monte Carlo methods to obtain answers that might otherwise have not been available. So let's start with a very simple example, the rolling of a six-sided die. In general, we can think about what are the chances that we roll a six on a fair six-sided die. We can know that without simulating different scenarios with our computer. Okay, we know the chance is 1 in 6, or about 16 or 17%. What about rolling two sixes in a row? Okay, we know that the chance of rolling two sixes in a row, if it's independent rolls, is 1/6 times 1/6, about 3%. Okay. We are deriving these values. We calculated 1/6 times 1/6 based on known mathematical properties and probability theory. But we didn't have to have any prior knowledge about these. That's relatively complex. We could just simulate scenarios. We can simulate the rolling of a dice a large number of times and estimate these probabilities. Okay. So we'll start here with a first look at sampling from just vectors. Okay. The sample function in R can be useful for randomly selecting different components of a vector, and this can allow us to simulate lots of different scenarios in real life, one of which being the rolling of a fair six-sided die. So each time we run it, we're simulating the roll of a dice. I got 1 on my first roll, 3 on the next, then 6, then 3, 4, 1, 3, 2, 6. and so on. You very likely did not get the same sequence of dice rolls as I did. These are being randomly generated, and so you will get different results for the roll of your dice at different times on different machines. Okay. The sample function in general randomly selects size number of values from a supplied vector. Here we're giving it the numbers 1 through 6. Okay. And it can do so by sampling with or without replacement. If we want to simulate multiple rolls at the same time, we can set replace equals true in the sample function to sample from this vector with replacement, because we can get a 6, for example, twice in a row. So the code below here allows numbers to be selected multiple times. So we're simulating 2 dice rolls at once. Okay. And we got 2 of the same number. I did at least 2 ones. Nothing too groundbreaking yet, right? Let's simulate, though, the roll of 100,000 dice rolls, storing the result in a vector called rolls. Okay, so we're going to copy the code from before. Instead of size equals 2, we're going to say 100,000. And we're simulating 100,000 rolls at once. R can do this nearly instantaneously, which is quite impressive. And then we can see what proportion of rolls were each number. Well, now that we have rolls, let's summarize it by first making an object called tidy rolls. Okay, into a tidy table called a tibble. That allows us to use various functions like the table function from the janitor package. Okay, so since we've already loaded all the packages above, we can use functions from the janitor package. For example, the table function, tabyl. Oops. Let's see. Oh, pipe it into table, and we tell table which column we want to tally up. Okay. So here's the results of my rolls. We have the value of each of the dice. N gives how many times that value occurred among my 100,000 rolls here. And then we have the percent. Notice that these are not exactly all the same. We got varying numbers for each of the dice values, although they're all roughly 16.6%. Okay. So this shows the inherent randomness in a Monte Carlo simulation. You get a Monte Carlo estimate of the true probability of getting each number here, but there is some error associated with it. It's not perfect. However, in general, if your simulation is properly designed, the larger number of simulations you do in total, the more accurate you can expect these Monte Carlo estimates to be. Okay. I also want to note here that the developers of the janitor package did a great job, but technically proportions are between 0 and 1, whereas percents are 0 to 100%. So this is really a proportion, not a percent. But it's a really nice package. It's nice it gives it to us so simply. So we appreciate them for that. Okay. So based on our Monte Carlo simulation here, we see, okay, with a fair six-sided die, yeah, we expect to get each value about 16 or 17% of the time. Again, nothing too groundbreaking. And we can even, yeah, nicely display this with flex table if we wanted, right, to get those values. Let's think about something that's a little slightly more complex. So let's consider runs of rolling a dice value that's the same multiple times consecutively. We want to summarize the different runs in our 100,000 dice rolls here. Okay. So we can do that using a handy base R function called RLE for run length encoding. This will summarize runs of consecutive dice values that are the same throughout these 100,000 rolls. Okay. I remember when I took an R programming class in graduate school, we had to do this manually, summarize the runs in a long vector of values, and it's not the easiest thing to do in a computationally efficient way. It's not easy to write a function that does this in a reasonable amount of time for something as long as like 100,000 or a million values. But the RLE function here is fantastic. So we get RLE here, tidy rolls. Actually, we can just use rolls. Just like that, we get runs. Okay. And then the RLE function is a base R function. So it gives us a not tidy objects. It gives us back what's called a list. And so here what this list is showing us that it's summarizing the runs in this vector of 100,000 dice rolls. So it's saying first we rolled a 2, and we only rolled one of those in a row. Then we rolled a 4, and we only rolled one of those in a row. Then a 1, and that was only once, a 6, and once, and a 3, and that was only once, and so on. Okay. It might take a while until you got to consecutive numbers. Okay, yeah, 16 or 17, we finally got 2 4s in a row. You can see that in the runs object as well. Okay, although it takes a while to get there. Yeah, not till the pretty far in do you get a run that's not just one single dice value in a row. Okay. So let's look at what are the most consecutive dice rolls of the same value. Okay, here what we can do is we can create a organized runs object. Let's call it like tidy runs. Let's see. We've got the lengths, and then we've got values. Yeah, and let's actually do values first and then lengths. You can say value equals runs, lengths. equals length. So we're using some base R syntax here where we've got a list, $sign, and then the name of the element in the list that we want. So the runs object is a list of length 2 that has two elements, lengths, and values. Okay, we organize that into a tibble, and then we can use the janitor package again in a similar way to before to summarize the runs. We're doing tidy runs now instead of tidy rolls. And then we can summarize the lengths. Oops, lengths with a capital L. So for me, in my simulation, here's the result of what I got. So a little over 69,000 times, we rolled a dice and we did not get the same value on this next subsequent roll. 11 or 12,000 times, we got the same value on the dice twice in a row, but then not a third time. Okay. 2,000 times, we got the same number 3 times in a row, and so on. And so you can see out of 100,000 rolls of the dice here, the most I got the same number in a row was 8 times. You might not have even gotten this many because, again, due to the randomness in how the simulation is implemented, we'll all get slightly different results. Okay. I'll even get different results if I rerun this code. Okay. There is a way, though, that we can consistently produce random numbers or random simulations in a reproducible way by using what's called seed values, which we'll talk about in a bit. Okay. So, well, actually, let's do that. Let's maybe right above where we've got our libraries here. Let's set a seed value using the set.seed function. Okay. A seed value serves as a placeholder for consistent random number generation from this point on down in your R program, in your Corto file. There's no inherent meaning to the number itself you use as your seed value when calling set.seed. It's advised that it should be a positive integer, but actually any numeric value is accepted, although nearly always people just choose a positive integer, but it's essentially an ID for that series of random number generation that starts at that point on down in your script. Okay, so often people choose like a favorite positive integer and just use that as a seed value that they tend to set when wanting reproducible random number generation. I like the year 1994, so that's what I use here, but you're welcome to use any positive integer you want. If you want to match the results that I'm going to get here exactly, you should set the seed value as 1994 at the top of your script here. Okay, then you run that, sequentially running each chunk once on the way down. If you set the seed to be 1994, you should get 2 on the first dice roll here, 3 and 2 in the sample function here, the second time we call it. Can you only run each thing once? Because if you run it more than once, you'll end up getting different numbers. Unless you go back to the top and start and work your way down, running each code chunk only once. Okay. All right. So when I use a seed of 1994, the longest run I get is 7, of length 7. Okay. And you should get these same exact numbers if you set the seed once and once only at the very top. Okay. So the total number of runs of each length is summarized in this table here with n. Okay. What's the ratio of the number of runs of length 2 compared to the number of runs of length 1? Let's look at that. Number of runs of length 2 to length 1. Here I get 0.1679. Looks familiar, right? This is awfully similar to 1/6. And theoretically, this number should be exactly 1/6. So if we had an infinite number of simulations, as opposed to just our finite 100,000 simulations here, this number would be exactly 1/6, right? In the long run, you'll get 6 times as many runs of length 1 as you do length 2. Okay, and that makes sense if we think about it from a number of angles, right? If you already have a run of length 1, essentially you've rolled a dice and gotten a single value on it. Okay, the chance that that extends to a run of length 2 is 1 in 6, right? And if you look at the number of runs of length 3 compared to length 2, we get a number that's slightly different, but it's also very similar to 1/6. You can keep on going down the line here, looking at the ratio of the count on one line to the count on the previous line, and you often get about 1/6. But notice what happens as you go further down into longer runs that were less common in our simulation. Okay, so for example, 50 over 308, 308 is still about 1/6. So that's the ratio of runs of length 4 and 5. 50 over 308, I believe. Yeah, that's still about 1/6. But what happens when you look at the number of runs of length 5 compared to 6? 9 over 50. Our number starts to deviate away from 0.16, right? 9 over 50. But this number truly is supposed to be 1/6. And if we look at the ratio of the number of runs of length 7 to 6, it's even worse, right? We get 3 over 9, okay, which is 1/3. That's almost double, right? It is double 1/6. This estimate is getting worse as we go looking at longer and longer runs because these are relatively rare events in our simulation. Okay, so this is a limitation of Monte Carlo simulations when emulating real life scenarios. If you're looking for exact probabilities or proportions involving extremely rare events, so something happening 3 times out of 100,000 simulations is very rare, right? then estimates involving these proportions can be quite unstable. In the long run, they should be unbiased, should be on the mark, but from simulation to simulation, there can be a lot of variability in this estimate. Okay. So if you're dealing with exceptionally rare events that you're trying to simulate with a Monte Carlo simulation, the main takeaway is that uh, you should look at how much your estimate varies by changing your seed value at the top, simulation to simulation, ideally hoping for some stability, right? And then potentially increasing the number of Monte Carlo simulations, if possible, to get a more stable estimate. There is a limit to how many simulations we can do, right? If I asked R to do 100 billion dice rolls, it just won't do it. R cannot handle that many numbers. Um, I mean, you can up it yourself and try and push R to the limit. It will depend on your own laptop typically, and R has its own constraints that it will impose on how long you can do your simulation for, right? How long it can be. Um, but for many cases, 100,000 simulations here is sufficient, right? It gets you pretty good estimates of things you are interested in. So let's look at a different part here. Continuing with sampling from vectors, we're going to work with this vector of fruits from the string-art package, okay, which should be available since we already have loaded the tidyverse. Okay. So let's try these parts out on your own. Pause your video, and then once you've had a chance to attempt them, come back, unpause the video, and we'll look at it together. All right, hopefully you had some time to try those out on your own. So let's take a look. If we want to select 10 values randomly from this fruit vector that's available from the string-R package, we can do this using the sample function, just like this. So we can say 10, and then we randomly select 10 of these fruit values. If you want to see them all, you can print fruit to the console, and there's 80 different fruits in here. Okay. So does the sample function use sampling with or without replacement by default? Well, we can't know for sure unless we got a duplicate fruit in here. Well, that's kind of hard to prove. One way to know for sure, if we look at the help file by submitting $sample in the console, okay, there we can see by default it samples without replacement. Okay, so it's not possible to get the same fruit. So it samples without replacement. So here we can sample with replacement by setting the replace argument to be true. Okay. Doesn't mean we necessarily will get fruits that are the same or duplicated here, but it's just possible now. Right, so we can keep rerunning this, and there, I got 2 blueberries. Right? You might get something slightly different depending on the order in which you ran things. To get the same result consistently, that's where again we can set a seed value. You can reset the seed value. We set one earlier at the top of our document to be 1994. And if we want to restart that consistent, reproducible random number generating process, again, we can reset the seed value. And now, so essentially, if you set the seed value in the same code chunk and ran this, you would get the same exact 13 fruits. Salal berry through mango. Okay, if you had replace equals false. We can see that in the activity, Salal berry through mango, right? Got the same 13 values, just like we did here. So that's a bit about how we can sample from vectors in R. We can also sample rows from tables or data frames. So the slice sample function is a function from the tidyverse that allows us to randomly select rows from a table of data. Okay. This can be helpful in a variety of settings, one of which is when you're working with very big data sets. It can be helpful, especially if you're under a time constraint, to use slice sample to get a random selection of, say, 1 or 10,000 rows from that table. Work with that to get all your code finalized for visualizations and summary statistics, and then run the code on the full data set at the end once you've gotten all your code squared away, right? This can be a really helpful approach, especially for like take-home data science interviews where they might have a significant time constraint on how long you have to analyze the data. So for example, here's this data set on fast foods. Okay, which we can import from the web. It has 10,000 rows and 11 columns. Certainly not too big to work with in R, but it's still a decently big data set. But we can use slice sample to explore random subsets of this data set, right? And there's a couple of different ways you can use this sampling. We can sample a fixed number of rows. So for example, we can randomly select 500 rows from this fast food table. Okay. And when we look at that, we get this sample data set that now has 500 rows. Maybe this is much easier to work with, less time consuming when fitting models or making visualizations. So we can just use this table instead. And then once we've got everything squared away, replace this table object fast food sample n with the full data set and rerun our code. Right? You can also randomly select a particular proportion of the rows in a table using slice sample. So the code is very similar, but instead of n, which specifies the number of rows to be randomly selected, you give the prop argument, which specifies the proportion of all rows that are to be randomly selected. In this case, we can do like 1%. And 1% of 10,000 is 100. So we get a random sample of 100 rows here. Okay. And so like I mentioned, using these random subsets of the original data, we can write code to make visualizations or calculate summary statistics, essentially generate insights about the data that are likely representative of the full data set because we randomly selected them. And if you choose a large enough number of rows that you randomly selected from it, it's likely that will mostly reflect patterns in the larger data set, though not fully guaranteed. Okay. But it's a great starting point, especially just when code can sometimes take a while to run for large data sets. Okay. So here, let's look at reproducing this table, showing the counts of the 5 most common restaurants. Okay, using this code here. Okay, so we can copy this code, which has this auto fit option now, this function that's called to make it fit nicely. Okay, so here's the 5 most common restaurants based on the 100 randomly selected restaurants from our sample. Okay, we can reproduce that table here. Okay, we get McDonald's, Arby's, Burger King, Taco Bell, Wendy's. Okay, and running this code like this. 22.9. Okay. And let's take a look at this. Okay, we've got 22.9976. And now that the seed values are the same in the activity, we get 22.9976. Okay, so we've reproduced it based on our small subset of the data, okay, just 100 restaurants. We've essentially estimated that McDonald's is the most commonly occurring restaurant, then Arby's, Burger King, Taco Bell, and Wendy's in that order, with Arby's and Burger King tied. Let's see how this shows up for the full data set. So here we can see McDonald's, Arby's, Burger King, Taco Bell, Wendy's. Roughly the same order, although Arby's falls down to 5th instead of 2nd. Burger King 2nd instead of 3rd, right? But we actually still have the same top 5 restaurants, not bad. The order's just slightly different. Okay, so let's reproduce this table from the activity for the full data set. Okay, so we've got the code that we used for this small subset, and we're just going to replace the table name with fast food, essentially using the full data set. Okay. So again, here for this data set, R can handle 10,000 rows, no problem. So it's not an issue to just use the full data set right out of the gate. We wouldn't actually need to do this exploration first with a smaller subset, but it can be helpful again if you have millions or hundreds of millions of rows. Sometimes R can be a little bit slow, so it can be very helpful in those types of settings, okay, for efficiency. Okay. Let's look at another big area of Monte Carlo methods, which involve sampling or generating values randomly from different statistical distributions. Okay. So in the field of statistics, if we're simulating data, a very common choice is to use the normal distribution, right? So this code right here generates 1,000 values from what we call a standard normal distribution. That's a normal distribution with a mean of 0 and a standard deviation of 1. Okay. Here, what we've got in this visualization is a histogram for these generated values, and then superimposed over it is this red density curve line showing the true theoretical density curve for the standard normal distribution. So we can see how our generated values, ideally, the true density curve would perfectly go through the tops of each of the bars in the histogram, but there's a little bit of roughness here. It's not perfectly smoothly going through all those bars. Okay, and that's because this is a finite sample of values that we've generated, only 1,000, not an infinite number of values from the standard normal distribution. Okay, but in general, it closely aligns to this bell-shaped curve, right? So using these 1,000 generated values, we could calculate different statistics or quantities associated with this if we are trying to emulate some type of real-life process where we expect values to come from a normal-like distribution, right? The normal distribution is a common one that shows up just because it shows up in real life things very often, right? And that's actually due to interesting mathematical properties about the normal distribution. There's reasons it shows up so often, but we'll just take it for what it is. However, it's not the only not the only useful distribution for simulating real life scenarios. So the normal is particularly useful for measurement errors, right? If we uh, measured everyone's heights here, and we did that repeatedly over time. Um, we all should be fairly constant, but the errors or the a little bit amount that were off in our measurements, if we recorded those over time, they would likely follow some type of bell curve shape. Other biological measurements, like if we measured our weights, right? If you plot the weights of all Grand Valley students individually, it tends to follow some type of bell-shaped curve, although potentially a little bit right skewed. Various values in econometrics, psychology measurements, different scores on exams. All these things just tend to follow a normal distribution. And again, there's mathematical reasons behind that, but if we want to simulate or emulate these different scenarios with a Monte Carlo simulation, we can do that by generating values using the R-norm function, which stands for random normal values. If you ever have a little bit more weight in your tails, in other words, there's extra uncertainty relative to a normal distribution, but your values are still expected to follow some type of bell curve that's symmetric. Student's t-distribution is a great is a great applicable distribution in that case. So this is useful in that the test statistic under the null hypothesis for the student's t-test follows a t-distribution. So if you wanted to simulate, what would happen if we applied a t-test a large number of times in the long run in this type of scenario, we can simulate that in part by using the RT function. Chi-squared test, right, most commonly shows up in the chi-squared test of independence, which allows us to test if two categorical variables have a relationship or not. There's also the chi-squared goodness of fit test, which can allow you to test if a set of values came from a particular distribution or not. Also, when estimating variances, right, if the original data was normal, the chi-squared distribution can come into play in regards to the sampling distribution of estimated variances. Okay. So all kinds of quantities the chi-squared test can be useful for. The exponential distribution is particularly useful for modeling time to events, especially when there's a reasonable assumption of a constant failure rate or a constant success rate, depending on how you view it. So it can be useful in certain settings where, yeah, that constant failure rate is a reasonable assumption. If you have a certain set of values streaming in that follow what's called a Poisson process, then the time in between events in that Poisson process are known to follow an exponential distribution, just theoretically. Other distributions that model time to event, the Weibull distribution. This one's particularly useful for survival analysis because it's a bit more flexible. It doesn't require as many assumptions as the exponential distribution. So I have a friend, for example, who graduated from Grand Valley and is an engineer, and he helps work on airplane parts, right? And so they will simulate time to failure of different airplane parts. And this can be a complex task when you have many parts on the same airplane that have different expected lifetimes, right? Different expected failure rates. And you might be interested in the interconnectedness of when one part fails, another part's up, and we hope that one doesn't fail in a certain amount of time, right? So simulating complex scenarios of many parts that are interplaying with one another, it can be helpful to use something like the Weibull distribution. So, right, when I chatted with him briefly about it, he indicated that yes, engineers very much like to use Weibull distributions for different survival analysis tasks. It's not the only way to model that type of data, but it's a flexible and useful distribution for many time to event scenarios like that. Okay, time to failure, essentially, of parts. So it's also useful in extreme value modeling, um, weather forecasting, right? Many things tend to follow this Weibull distribution. It's a non-negative distribution. If you Google the Weibull distribution, the Wikipedia page is great for many different statistical distributions. Um, here it gives like the theoretical probability density function, the PDF of the Weibull distribution that essentially defines the density curve, which shows us where values are likely to occur. And this density curve can look different ways depending on the different parameters, right? So for the Weibull distribution, we have two parameters, lambda and k here. Each of these distributions has their own sets of parameters that uniquely define it. For the normal distribution, it's the mean and the standard deviation, or equivalently the mean and the variance. For the t-distribution, it's the degrees of freedom. Chi-squared, degrees of freedom, exponential distribution, lambda. Weibull has those two parameters, right? So those are things you could estimate from your data or preliminary studies if you need to decide how you should be generating your values, right? Or just known, right, doing like a literature review, your own research to find out what typical parameter values would be for your data that you're interested in. The F distribution most commonly arises, probably you've seen it before, in ANOVA, analysis of variance. The test statistic under the null hypothesis follows an F distribution. Also useful for testing nested models against one another in multiple linear regression. The beta distribution is particularly useful for modeling proportions because it's bounded between 0 and 1. So this can also be useful in Bayesian statistics, where you have hierarchical models potentially. Uniform distribution is an interesting distribution that arises in a lot of different concepts. It's essentially for the continuous uniform distribution, you assume that the numbers can come anywhere between two values A and B, and any number is equally likely anywhere in between. Okay. That shows up in a lot of different real life scenarios. For example, if you assumed that the Laker line comes every 10 minutes to the bus stop, and you randomly show up to a bus stop on a day without paying any particular attention to the time or the bus schedule, then your expected waiting time until the next bus comes would be uniformly distributed between 0 and 10. You can wait anywhere from 0 to 10 minutes. Any time in there is equally likely. In the long run, if you did that many times, the expected value or mean is going to be 1/2 times A plus B. In that scenario, with the Laker line coming every 10 minutes, that would be 1/2 times 10 plus 0, it's 5. So your expected waiting time in the long run would be 5 minutes, exactly in the middle. Okay. And then just a couple other distributions. There's so many, and this is not an exhaustive list by any means, but the binomial distribution is particularly useful for logistic regression and classification models. The negative binomial is useful for modeling count data, especially when you want a more flexible variance structure for the data than, say, a Poisson distribution allows. So civil engineers, it's common to use the negative binomial, um, quality control settings, epidemiology, where you're modeling disease counts, right? When I worked on a project trying to model um, pandemic outbreaks in graduate school, I studied biostatistics, so we would work with epidemiology graduate students, and I remember they were always like quick to turn to the negative binomial. They were like, "Oh, we're modeling disease counts, disease outbreaks. Negative binomial is great for that." Um, and yeah, Poisson distribution also great for modeling counts, but not as flexible with the mean variance relationship as the negative binomial. And then the gamma distribution can also be used to model time to event or survival analysis. So it can be useful for insurance companies modeling claim sizes, modeling things like rainfall, and also in lots of Bayesian hierarchical models. Okay, so lots of different statistical distributions that are useful in a variety of settings. I tried to make this table just as like a reference for you. I've never seen anything like this before on the internet, but I thought it was a useful, uh, table of organization to have just regarding different distributions you can use for different settings, right? So whenever you're deciding what distribution you should use, if you're trying to simulate a particular setting, there's lots of things you should consider. The type of data, is it continuous, discrete, ordinal, or nominal? Lots of times that alone will constrain it down to just a couple distributions you can pick from. The bounds of the variable that you're interested in simulating, right? If it has to be between 0 and 1, then you're really only left with a couple options, probably the beta distribution or the uniform distribution, to name just a couple. But if it's 0 to infinity, there's a whole bunch of options then. Um, yeah, the shape and spread of the data, how much variability there is. And so with all these factors considered, there's a lot of choice along the way in terms of choosing what distribution you want to generate from. So how can you know if you've made a good decision? Well, fortunately, it's not all subjective. If you have some observed data, if you have a little bit of actual observed data from this phenomenon that you're trying to simulate, you can use metrics like Akiki's information criterion and the Bayesian information criterion, AIC and BIC, to assess model fit. Essentially, if you try out two different distributions for your data, you can calculate the AIC values for each of those, and in general, a lower AIC value indicates better fit of that particular distribution. Okay? And similarly for BIC, you can calculate the BIC, say, assuming the data came from a normal distribution, and then the BIC for assuming the data came from a gamma distribution. And then whichever one ends up with a lower BIC theoretically has better fit, and so that's the better choice of distribution. You can also visually inspect the data plotted using what are called quantile plots, QQ plots, which we'll look at later. And that's just a visual way to see how well that particular distribution fits the data that you've observed. Okay. All of these functions generate independent values from these different distributions, but there can also be, in many real-life scenarios, correlations or other dependencies inherently structured in the data. Can be over time, right? If you have stock values over time, those are very much related temporally across time. You can also have spatial dependencies. If you're looking at poverty rates for each of the 50 US states, right? States that are closer together are more similar typically. So they're not independent. So lots of different ways that additional complications can be something that you should account for when simulating real life scenarios. Um, So it needs to be adequately considered. Okay, so when using any of these functions, like I mentioned, we have to specify or know the parameters that we want to use for that distribution. For the normal, for example, that's the mean and the standard deviation. We also have to specify the number of values that we want to generate from that distribution, okay, given by lowercase n. If you want to see what exactly the parameters are that you need to specify for a distribution, you can submit question mark and then the name of the function for generating from that distribution to the console, and it will tell you what the arguments are. Or probably nowadays you could, ask AI as well, and it would probably do fairly well. Okay. So let's, instead of just continuing to talk about these different distributions, let's actually use some of these functions. So for example, let's get a Monte Carlo estimate of the median of the standard normal distribution by generating 100,000 values from it. Okay. Maybe we'll call it like normal values, R norm. Okay, we want 100,000, a mean of 0, and a standard deviation of 1, since we're wanting the standard normal distribution. These are the default values. If you look at R norm, it defaults to the standard normal distribution right here, but it doesn't hurt to specify it explicitly. Okay, so we can generate those values and then getting a Monte Carlo estimate of the median, the 50th percentile. Okay, we can do that using this quantile function. And then we can say probs equals 0.50 to say the 50th percentile. Okay, so we generate these values. Again, you might get a slightly different value depending on where you set your seed value. If you wanted to reset the seed value right above where you generate these 100,000 values, that would ensure that you get the same exact Monte Carlo estimate, which would be minus 0.003. Okay. Theoretically, if we look up the normal distribution, the normal distribution is what we call a symmetric distribution. In other words, if you took its density curve and you sliced it in half down the middle, it's the same reflected either way. Symmetric distributions have a nice property that the mean is always equal to the median. And in this case, the mean is given by mu, so the median is the same. So theoretically, we generated these values to have a true mean or expected value of 0. The true median, therefore, we know must be 0. But we're seeing how we can get a Monte Carlo estimate in case we didn't actually know that, right? This number, right, the fact that the median is mu, not only is based on the property that it's a symmetric distribution, but you could derive this mathematically by using an integral of this PDF function here, probability density function, okay? If you don't want to do calculus, if you don't want to calculate definite integrals, Monte Carlo estimates can get you a pretty good numeric estimate of the value you're interested in, right? We can also use the median function here, and that would give us the same answer. Okay. But the quantile function is more general. You can get any percentile, not just, oh, actually, it shouldn't say probs there. Median function does not take that argument. Surprised it didn't throw me an error. Okay. But the quantile function is more general. You can get any percentile, and you can even get a vector of percentiles if you give a vector of proportions to the probs argument. Okay. So let's see how we can calculate an estimate of the 97.5th percentile. Again, using the quantile function. Okay. So Monte Carlo estimate of the 97.5th percentile is 1.962. Looks familiar maybe, right? This is the same as our confidence interval multiplier. You may have seen this in an intro stat class. Confidence interval multiplier for a 95% confidence interval. Okay. Now, this is just a Monte Carlo estimate of that number. It's not exact. Actually, if you wanted to get the exact 97.5th percentile, we can use the Q norm function to get different quantiles of the normal distribution. True theoretical value. Okay, therefore we can get like this. So here's the theoretical 97.5th percentile of the standard normal distribution. Now notice R truncated this here. It's actually an irrational number, so it goes on forever with no repeatable pattern. So actually, even though we use 1.96 in many of our intro stat classes, right? That's actually just rounded because out to even 4 decimal places, that's fine. And that's good enough for pretty much most all cases, right? All right, so next, let's consider a slightly more complex scenario that we can use a Monte Carlo simulation to estimate quantities about. And this one's going to be involving potentially familiar cartoon character, SpongeBob SquarePants. So we're going to suppose that SpongeBob SquarePants is waiting for a bus at rock bottom here, right? And he wants to catch this bus back to Bikini Bottom to go to his favorite restaurant, the Krusty Krab. His bus comes every 20 minutes. And therefore, if SpongeBob randomly shows up to the bus stop, which we're assuming, his waiting time is going to be uniformly distributed between 0 and 20 minutes. Okay. Again, note that there's lots of different options for modeling waiting times, including the uniform, exponential, and Weibull distributions. You can actually also use the gamma distribution. But here in this setting, the uniform distribution makes the most sense, so that's what we're going to use. So let's use Monte Carlo methods to answer the following. If SpongeBob just arrived at the bus stop, what's his expected or mean waiting time until the next bus comes? So first, what we need to do is simulate this scenario. So let's decide how many simulations we want. I think we have a choice. Yeah, we have a choice. Okay, let's do 10,000. And yeah, let's make an object called waiting times. So we're going to use runif. Runif takes 3 arguments, n, min, and max. N is going to be the number of values we want to simulate, which will be n simulations here. Min is the minimum parameter for the uniform distribution. Here that's going to be 0. SpongeBob at minimum has to wait 0 minutes, and at most he has to wait 20 minutes. And we can, yeah, to get the same exact simulations if we wanted, we could reset the seed again. Usually, if you're doing one analysis or one Monte Carlo simulation, you might just set the seed once at the top because we're doing kind of several distinct things here. We're just resetting the seed just to make it easier for you all to get the same exact numbers as me if you feel more comfortable. So here, yeah, we're simulating SpongeBob waiting for the bus. Here was our number of simulations. Right, we're being good coders. We're using comments. All right, to explain what our code's doing. Okay, so we've simulated SpongeBob waiting for the bus 10,000 times. And now if we want to get an estimate of SpongeBob's expected waiting time, we can use the mean function. The mean in theoretical statistics is the same as the expected value. We get 9.92 minutes. Okay. This is based on 10,000 simulations. That's a pretty good estimate. The uniform distribution, as we saw earlier, there's actually a lot known about it. This is the continuous uniform distribution. The mean or expected value is 1/2 times a plus b. Okay, so we know that that theoretical value is 1/2 times a plus b. So 0 plus. The true theoretical value is 10, but our Monte Carlo estimate's 9.92. It's pretty good, but not perfect, right? We didn't need any calculus or theory knowledge to get this. So yeah, some benefits there. If you were working with something as simple as the uniform distribution, you would, of course, just look up the theoretical value. But yeah, just showing how we can get Monte Carlo estimates of different parameters if we didn't know them here. Let's think about what's the median waiting time until SpongeBob next comes for the bus stop. So we could use either the quantile function or the median function here. We'll just use median. So we get 9.89. Okay. Now, let's complicate things slightly more for this SpongeBob scenario. So we're going to add in his friend Patrick. So we're also going to suppose that Patrick wants to go back to Bikini Bottom with SpongeBob. So before SpongeBob can catch a bus, Patrick first needs to get to SpongeBob at Rock Bottom. And Patrick is coming from Glove World at his own bus stop that he's waiting at to first go to SpongeBob. So you can click on this scenario here. Okay. And so we've got Patrick waiting at his bus that comes every 30 minutes, which is also uniformly distributed. Once his bus comes, he then rides on it, and we'll assume it takes exactly 10 minutes to then get to SpongeBob. So Patrick waits, rides the bus, gets to SpongeBob. Once they're there together, then they have to wait with their uniform distributed waiting time between 0 and 20 minutes to catch the bus to head to Bikini Bottom and ultimately get to the Krusty Krab here. We're going to simulate this whole chain of events, this whole scenario using a Monte Carlo simulation. Okay. So to get to this final point where they're on the final bus, what's the total expected waiting time for SpongeBob? That's what we want to find out. How can we do that? Well, first, we're going to simulate the extra legs of this trip. Oops. Okay. There we go. We're going to do that using the mutate function. Let's first simulate Patrick waiting for his bus. Okay, so Patrick waits for his bus, and his wait time is distributed uniformly between 0 and 30. 0 to 30, same number of simulations. Okay, that gives us Patrick's. Once we have Patrick's waiting time, that takes him 10 minutes to get to SpongeBob. And then 20 minutes, 0 to 20 minutes uniformly distributed is the wait time here once they get to rock bottom. Okay, so how can we get their total waiting time? Until they're on a bus heading towards Bikini Bottom, towards the Krusty Krab. Well, the total waiting time is given by Patrick's first waiting time, which is random, plus 10 minutes for his bus ride, plus SpongeBob's random amount of waiting time. So in other words, the total waiting time is given by Patrick's waiting time first, plus 10 for his bus ride, plus SpongeBob. Okay, that was the name of the variable from before. That gives us our total waiting time. And we're assuming implicitly in how we generated this data that their different waiting times are independent of one another. In real life, if Patrick's bus is late, it's probably related to whether SpongeBob's bus is late or not. Those are not likely independent events. So you would truly need a little slightly more complex simulation to handle that, but here we're going to keep it simple and assume everything's independent. Okay, so now that we've simulated the total waiting time, we can answer these questions, or get estimates, at least. What is SpongeBob's expected waiting time until they're finally on a bus heading to the Krusty Krab? Okay, we can do this by calculating the mean of the total simulated waiting time. $35 about. Okay, and theoretically we could derive that, and it should be exactly 35 minutes, but our Monte Carlo estimate is not far off. Okay, what about the median? Okay, we have the median, 34.81. It's very similar. Okay, notice that this also should theoretically be exactly 35 minutes. There's just a little bit of error, inaccuracy associated with our Monte Carlo estimate, but not bad at all. And if we upped the number of simulations from 10,000 to say 1,000,000, this estimate would nearly certainly get more accurate. So let's answer some more complex questions about their trip now. Using the quantile function, for example, we can estimate things like the 99th percentile of a set of values. We can use that here to get a Monte Carlo estimated 95% confidence interval for the total waiting time in minutes for SpongeBob until a bus comes for him and Patrick to take them to the Krusty Krab. So this is not a confidence interval for the mean, it's a confidence interval for the individual waiting times, okay, for them. So using the quantile function here, oh, was the median. That was the mean. Yep. Okay. Yeah, we're going to use the quantile function here. And to get a 95% confidence interval, we have to think about what percentiles correspond to the bounds of the 95% confidence interval. Okay. So for example, if we have a distribution curve here, and we want the middle 95% of this distribution, conventionally, we opt for the middle 95% of the distribution of values here. What that means is we've got 5% in the tails. Okay, so 0.025 in that tail and 0.025 up here. My handwriting's not the best with the Zoom annotation tool here, but what this means is that this is at 0.025. Actually, maybe I can just that means that this value is at 0.025, and this other value way over here is at 0.975. Okay. Those are the two percentiles that correspond to the cutoffs for the middle 95% of the data. This is what we call a symmetric confidence interval because we have equal sized tails on the outside of our confidence interval here. Okay. But note that you could take just the first 95% of the chunk of this distribution and leave off just the top 5%, and that would give you different bounds. But it's also a valid 95% confidence interval here. Okay. It's just not a symmetric tailed one. Either one's valid, but nearly always you'll see people opt for this or default to using this symmetric 95% confidence interval because we have more values in here. We have more data to estimate the 2.5 percentile as opposed to the absolute minimum of the data, right? If you have generated even 100,000 values from a distribution, right, it's impossible if it's a continuous distribution that you have observed the true minimum, right? So in general, just these will provide more reliable bounds using a symmetric 95% confidence interval. But I just wanted to point out that there's other types of confidence intervals out there. Okay. All right. So here we want 0.025, 0.975 for our symmetric 95% confidence interval. Okay. We get 15.6 to 54.4 minutes. And now we'll interpret this interval. Okay. So what we can say, let's start with just interpreting well yeah, let's interpret this interval. Okay, so we can say that we expect, let's see, I want to make sure I phrase this properly. We expect SpongeBob and Patrick's total waiting time in minutes to be between 15.6 and 54.4 minutes, 95% of the time. And we can even use inline R code to dynamically include these numbers in our text. Okay, so we can say we expect SpongeBob be between, and then we can use these single backticks, which are right next to the 1 on your keyboard, a little lowercase r. RStudio tends to autocomplete the backticks, so you got to be careful about that. And yeah, if we have an object called like CI limits up here that we make, then the first element of CI limits will give the lower bound. Here's what we can do. Be between this and upper bound 95% of the time. Okay. And if we wanted to round this, we could round it to say 2 decimal places using the round function. Okay. It's a reasonable amount of precision, right? 2 decimal places, that's good for many different settings. You often don't want to include too many decimal places because it can imply a false sense of greater precision than you actually have, right? So here's how it looks, the inline R code in the raw document. After we render this, okay, we can see how this looks rendered. It shouldn't dynamically include these numbers in our sentence here, which is nice. Right there. Dynamically included those numbers in our interpretation. It's a great way to have a more reproducible analysis. Okay. All right. So let's see. Okay, before we try this you try part, let's next visualize each of the waiting times for SpongeBob, Patrick, and the total waiting time. Okay. So if we go back up when we first generated SpongeBob's waiting time, let's add in a visualization. Okay. So this is a single quantitative variable. There'd be a couple common visualizations you could use for this, either a histogram or a box plot. We're going to opt for the histogram here. Okay, so we're going to use our trusty old ggplot, specify X to be SpongeBob's waiting times, and then add our geom histogram to get that histogram here. Okay. Oop. But we'll try and spell it correctly. There's our histogram. Okay. By default, Hadley, the developer of the ggplot2 package, has the outline color of the bars be the same as the fill. Okay, here we'll override that default so that we can better delineate the bars in the visualization. We'll make the bars not floating. And then we can add descriptive labels to the plot, right? SpongeBob's will say like simulated waiting times. And then note that count and frequency are synonymous terms. Either one's fine. And this is the waiting time in minutes. Important to specify the units of measurement when you can here. Great. And this gives us the distribution of SpongeBob's waiting times. Note that the uniform distribution, all the values are equally likely, but just by construction of how a histogram is made, you'll notice that the bars on the tail ends are shorter. It's not that those values are less likely than the other values, right? That's just how the histogram does binning. That's how the bars end up being displayed. But all values, when generating from a uniform distribution, all values between the min and the max are equally likely. Okay. So there's nothing wrong with this plot as it is, but we can make it a little more SpongeBob-esque, right? A little bit more in SpongeBob's style. So let's do that by just adding some custom SpongeBob colors, right? One way to do that is to use hex codes. So hex codes are unique IDs for very specific colors, such that they'll be consistent across different software tools or different programming languages. There's free online tools or other ways that you can extract hex codes from different images, right, to get the exact hue that you're looking for. So here what we're going to do is get a quick look at SpongeBob, and we're going to extract, let's see if that's a good one. Okay, and if you right click and do copy image address, that can be useful for this particular hex code color picker. You can say use your own image, and you say I want to give an image URL. And let's see if that works or not. Okay, that worked. Great. And so we can get SpongeBob's very particular yellow here, right? And in our code, what we can do is say, oh, we want the fill of the bars to be this color. And then maybe, so that's more SpongeBob-like, but then maybe we want the outline color of the bars to be like the brown of SpongeBob's pants. So then we can get the brown from his pants and do that as well. Okay. Perfect. Now it's a little more SpongeBob-like, which is just kind of fun. And you could do this, of course, with like maybe your company logo has a very particular set of colors with it, and you want to use those in visualizations. Using hex codes is one way to do that. So let's visualize Patrick's waiting times as well, just for his own bus, right? So we'll update the code to say Patrick instead, Patrick's simulated waiting times. And his bus came every 0 to 30 minutes. So this plot's not wrong, but there's something we should update, right? These aren't Patrick's colors, these are SpongeBob's colors. So let's get Patrick. And his name's Patrick Star. So copy image address for Patrick Star. Use our own image URL. Okay, great. And let's see. For Patrick's, let's use the fill as like his pinkish. And maybe like his purplish as the outline color. But you can do whatever floats your boat. Here we go. Yeah, now that looks a little more Patrick-like. And then we can simulate the total waiting times as well. And let's use maybe SpongeBob's colors since he's the main character. And so we'll have total time instead of SpongeBob here. SpongeBob and Patrick's. Total simulated waiting times. And you notice you have this kind of triangular trapezoidal shape, I guess. Okay, so we ended up with a complicated function of Patrick's waiting time plus 10 plus SpongeBob's waiting time. Okay, evidently we end up with a distribution that's not a uniform distribution, and here's what it looks like. So we might not know as many properties about what this distribution is or theoretical properties about it, but we don't care. We got Monte Carlo estimates of its mean, of its median, and even a 90, like the estimates of the 2.5 percentile and the 97.5th percentile without knowing anything about this distribution. Just our Monte Carlo methods and our computing skills here. So lastly, let's just try this with this different, slightly different distribution out. Oh, I guess we can render this. But yeah, we're gonna have this last try part where we'll generate a million values from a gamma distribution with shape and rate parameters. Okay, so pause the video, try this out on your own first, and then we'll look at it together real quick. Okay, and then looking at this, here's how we can generate 1 million values from a gamma distribution. R does that nearly instantly with a shape parameter of 3 and a rate parameter of 1. And then we can get a Monte Carlo estimate of the median, which is 2.67 here. This is particularly interesting because if you look at the gamma distribution, here's what the median is, okay, from theory. If you look up the median for the gamma distribution, no simple closed form exists. There's not a straightforward simple formula. Okay. Again, we could calculate based on an integral of the PDF function, the probability density function here, a definite integral. We could calculate the median value given the shape and rate parameters, but no calculus required here. With a million values, we can get a pretty reliable estimate of the median of this gamma distribution. Okay. So even in a relatively simple scenario like this, we can get a quick Monte Carlo estimate that's quite useful. Okay. So this last part is optional, but I would encourage you to try it where you calculate more Monte Carlo estimates. Okay. But that's it for this activity where we learned about Monte Carlo methods and simulations with R. Thanks.